Come on, my dears, let us proceed further in the chapter number 4. Last time we had studied what is called polarization. Remember? Process of conversion of unpolarized light into plain polarized light is called polarization. Fine. Now, this polarization can be made possible of unpolarized light through various ways. There are various means and ways for making the light polarize. One of such methods we have studied last time, that was using a tourmaline plate. Now today we will study another method of making the light polarize, that is polarization by reflection. And this method was devised by scientist Mr. Malus in the year 1809. Mr. Malus in the year 1809 had proved practically that on the surface of some denser transparent medium, when we make the light ray incident, it so happens that reflected light becomes partially plane polarized. Look, we make incidence of unpolarized light and then we get reflected light. We find that this reflected light ray becomes partially plane polarized. That is, majority E vectors oscillate mutually parallel. Okay, fine. When majority E vectors are oscillating parallel to each other, naturally that light is said to be partially plane polarized. But then, if you make this ray incident at some definite angle of incidence, it so happens that this reflected light ray becomes completely plane polarized. And when it is becoming completely plane polarized, it has to have all the E vectors mutually parallel. Yes, those E vectors are found to be mutually parallel and all of them are oscillating this way, means perpendicular to this plane of incidence. What is that plane of incidence? A plane passing through incident light ray, normal drawn at the point of incidence, and reflected light ray is called plane of incidence. And when this reflected light ray becomes completely plane polarized, all E vectors are found to be oscillating in a direction perpendicular to this plane of incidence. Okay, fine. Now, when reflected light ray becomes completely plane polarized, that becomes possible at some definite value of angle of incidence. That definite angle of incidence is called angle of polarization. It is called angle of polarization. It is shown by symbol theta p. P you must write below theta. That's why I have written here I equals to theta p, because right now this reflected light ray I am going to show completely plane polarized. How would you define angle of polarization? Very simple. If a ray of light is made incident at a particular angle of incidence on the surface of given denser transparent medium, then reflected light ray becomes completely plane polarized. That very angle of incidence is called angle of polarization for that denser transparent medium. Okay. A definite value of angle of incidence of incident light ray at which reflected light ray becomes completely plane polarized is called angle of polarization. I repeat, a definite value of angle of incidence for a ray of light made incident on the surface of given denser and transparent medium at which reflected light ray becomes completely plane polarized is called angle of polarization for that transparent medium. Okay, shown by symbol theta p. Fine. Now tell me, this is incident light ray, this is reflected light ray, and this one is refracted light ray. Refracted light ray. Angle made by refracted light ray with the normal is called angle of refraction. Let it be shown by symbol R. I is angle of incidence, theta p is angle of polarization, r is angle of refraction. And now look here, the incident light ray is unpolarized, and because it is unpolarized, it has to have all the E vectors oscillating in all the possible directions in a plane perpendicular to direction of incident light ray. Think of a plane like this, then in this plane all these E vectors are oscillating in all possible directions. Now every E vector can be resolved into two mutually perpendicular components. One is that component which is perpendicular to this plane of incidence. The one which is perpendicular to the plane of incidence, it is called sigma component and is shown by symbol of dot. Okay. And another component which is parallel to plane of incidence is called pi component, which is shown by symbol of line. So these symbols indicate pi components, and these dots, they indicate sigma components. When angle of incidence is equal to angle of polarization, this reflected light ray becomes completely plane polarized. Not only that, all the E vectors in that are having only sigma components. That is, they are all perpendicular to this plane of incidence. All of them are perpendicular to the plane of incidence, so all of them have only sigma components. Fine. Now, if this denser transparent medium is glass, then proportion of sigma components is found to be 15%, approximately 15%. Now here there are 100% sigma components, 100% pi components. Out of 100% sigma components, 15% is obtained here in the reflected light ray. Remaining 85% of sigma components is obtained in the refracted light ray. Here not a single pi component, that's why all 100% pi components are present in the refracted light ray. Fine. This I am talking about glass. Okay. Fine. Now there was a scientist with name Mr. Brewster. What he had proved practically that when a ray of light reflected from the surface of denser transparent medium becomes completely plane polarized, at that time the angle between reflected light ray and refracted light ray is found to be 90 degree. Is found to be 90 degree. So that angle is 90 degree, which are shown here. Okay. I repeat. When a ray of light reflected from the surface of given denser transparent medium becomes completely plane polarized, at that time the angle between reflected and refracted light ray is found to be 90 degree. Fine. Now use this fact and obtain one result which we will call Brewster's law. What is that Brewster's law? I am showing you. Come on, what is this angle? Actually it is angle of reflection, but it is equal to angle of incidence. And angle of incidence is right now, come on, I equal to theta p. So this angle is also theta p. This is 90 degree and this one is small r. If you make addition of all these three angles, that addition would be this much. This much means how much? This much means 180 degree. So this plus this should be 180 degree. Come on, theta p plus 90 plus r. Theta p plus 90 plus r should be 180 degree. And now transfer this 90 over here. 180 minus 90, that is 90 degree. And transfer this theta p also here. So r will be equal to 90 minus theta p. 90 degree minus theta p. Value of r is r equals to 90 degree minus theta p. And now apply Snell's law for refraction of light ray taking place at point B. Apply Snell's law. Upper medium we take as first medium. Its absolute refractive index I am taking n1, and if it is air or vacuum you may take n1 equal to 1. And lower medium is second medium. It is denser transparent medium whose absolute refractive index I am taking as n2. Let it be shown by symbol n. Fine. Now Snell's law is this: n1 sin theta 1 equals to n2 sin theta 2. Come on, n1 is 1. n1 is 1 into sine of theta 1, where theta 1 is angle of incidence in the first medium. It is I, but I equals to theta p. So instead of theta 1 I am writing I. Okay, angle of incidence. And now n2 is n. n2 is n. n2 is n. Sin theta 2. Theta is 2 is angle of refraction in the second medium, which is right now small r. And now tell me, I is also equal to theta p. So put it here, I equals to theta p. I equals to theta p. This n as it is, sin as it is, r equals to 90 degree minus theta p. R equals to 90 degree minus theta p. R equals to 90 degree minus theta p. Now this sin theta p as it is, n as it is, sine of 90 degree minus theta p, it is nothing but cos theta p. Find out n now. It will be sin theta p upon cos theta p. Sin theta p upon cos theta p is nothing but tangent of theta p. And tell me, what is theta p? After all, it is some sort of angle. So I may write angle of incidence, angle of incidence. So I may write I. So write just theta p equals to I. Theta p equals to I. So n equals to tan theta p or n equals to tangent of I. This very result which was derived by Mr. Brewster, in his memory we call it Brewster's law. Tell me, how would you give the statement? When a ray of light reflected from the surface of given denser transparent medium becomes completely plane polarized, comma, the tangent value of angle of incidence gives us value of absolute refractive index of that transparent medium. I repeat, when a ray of light reflected from the surface of given denser transparent medium becomes completely plane polarized, comma, the tangent value of angle of incidence is equal to refractive index of that denser transparent medium. This very statement is called Brewster's law. I repeat, when a ray of light reflected from the surface of given denser transparent medium becomes completely plane polarized, the tangent value of angle of incidence is equal to refractive index of that medium. This very statement is called Brewster's law. If surrounding medium is air or vacuum, then you may take this as absolute refractive index. If surrounding medium is some thinner medium, thinner than this medium, then this is denser, the surrounding medium may be rarer medium. Then you are supposed to take here relative refractive index of thicker medium with respect to thinner medium, or relative refractive index of denser medium with respect to rarer medium. Suppose a ray of light is entering from water into the glass, At that time, that ray is getting reflected from the surface of glass. At that time, you should write here, come on, refractive index of glass with respect to water. Refractive index of glass with respect to water, okay? And if surrounding medium is air or vacuum, you may take this as absolute refractive index, okay? I repeat the statement once again. When a ray of light reflected from the surface of given denser transparent medium becomes completely plane polarized, the tangent value of angle of incidence is equal to refractive index of that medium. This very statement is called Brewster's law, okay? Fine. Now let us see some of the uses of polarization. First of all, what is historical use? Remember, before this polarization, in the same chapter, we had studied about interference and diffraction. Now, interference and diffraction are those phenomena which are possible even for longitudinal waves. They are possible for longitudinal waves also, they are possible for transverse waves also. Now, polarization is the only phenomenon which is possible only for transverse waves. It is not possible for longitudinal waves, correct? If light waves would have been longitudinal, then polarization would not have become possible for light. But polarization of light is possible. It shows that light waves must be transverse in nature. So we have come to know that light waves are transverse in nature. Through which phenomenon? Through the phenomenon of polarization. This fact gives you historical use of polarization. Got it? Fine. Second use, to study some properties of a body. What we do practically, we just get the emission of light from some body, or we get scattered light from the surface of the body. and then we study the state of polarization for such a light, and from that study we can just study the properties of that body. Fine. Then around the planet with name Saturn, around this planet which is known as Saturn, we have circular rings made up of crystals of ice, but that thing we have come to know from the study of polarization. Okay, fine. So rings around Saturn planet, they contain ice crystals. This fact we have come to know through polarization of light. Then volume and shape of different viruses are determined from the ultraviolet light scattered from their surfaces. Okay, we have come to know about volume and shape of viruses. Then in the study of atom and nucleus, light which is used sometimes, it is polarized light, and using that polarized light we study some of the properties of atom and nucleus. Then to know about type of sugar and about concentration of sugar solution. Using polarized light we can just determine the type of sugar, quality of sugar, and also the concentration of sugar solution. Then calculators, TV, laptops, watches, they have certain specific type of screen which is liquid crystal display, and in just preparing that we are using the polarized light. Okay, that construction is called liquid crystal display. They employ polarized light. Fine. Then in the sunglasses, see when you just observe some focused light, then there may be some damage to your eye. You cannot just watch that focused intense light with your naked eye. Okay, at that time if you have just put on the spectacles, say sunglasses, at that time what happens, that light which is getting reflected from some shining surface, it is having so much of intensity that may cause damage to your eye. But now because you have put on those sunglasses, ultimately those E vectors which are oscillating perpendicular to the optic axis of that sunglass will be getting absorbed, and so finally intensity of light entering into your eye will be diminished, and if just proper intensity is entering in your eyes, then your eyes will be saved from the possible damage. This is again application of polarization. Correct? Fine. Then in the study of one phenomenon called stress and strain, about which you will study, you have already studied in second semester about stress and strain. When we study this phenomenon about stress and strain in case of glass or bakelite, at that time we employ one method which is called photoelasticity. Correct? And in the method of photoelasticity we use polarized light. Okay, so these are the various uses of polarization which you must remember. Okay, now kindly read the statement of sum number 10, illustration number 10. Just read it. Come on, have you read it? Look, we have one tourmaline plate on which we make incidence of unpolarized light having intensity say I0. Then what would be intensity of emergent light ray? What would be intensity of transmitted light ray? That is what we have to find out. Fine. Let it be I. Okay. Here, because the light ray is unpolarized, it would contain E vectors in all directions with equal number. So E vectors are equally arranged in all the directions. Then if any given E vector makes angle theta with this optic axis, then the theta would change from 0 to 360 degree. In one circular rotation, come on, it would have angle made with optic axis changing from 0 to 360 degree. 0 to 360 degree means 0 to 2 pi radian. 0 to 2 pi radian. Fine. Now, in that case, what will be the intensity of emergent light ray? It would be average intensity. And that average intensity you may write according to Malus law. You know I equals to I0 cos square theta. I equals to I0 cos square theta. But in that format of Malus law, what was theta? It was angle between two optic axes of two tourmaline plates. Here there are no two tourmaline plates. There is only one tourmaline plate. Then you should take this theta as angle between incident E vector and optic axis of a single tourmaline plate. That angle is theta, which is likely to change from 0 to 2 pi. 0 to 2 pi radian, correct? Fine. Now, because I0 is constant, I can take it out, and now average of cos square theta. Average of cos square theta. Now, this I0 as it is. We want this average of cos square theta over the range of theta from 0 to 2 pi radian. And for that, finding that average value, what you should do? Right from 0 to 2 pi radian, for each angle value, you should find out the value of cos square theta, and then such value should be added up. That is, mathematically you should go for taking integration, and then that summation should be divided by same interval of angle. That interval of angle is from 0 to 2 pi radian, that is, it is 2 pi radian. So, this summation is divided by same angle 2 pi radian, then it will give you average of cos square theta in that interval of angle. Fine. Now, this I0 upon 2 pi I have written here, and integration as it is, but cos square theta formula is, you know, it is 1 plus cos 2 theta by 2. 1 plus cos 2 theta by 2 d theta. And now I0 upon 2 pi into 2, that is 4 pi, integration 1 d theta, integration 1 d theta, plus integration cos 2 theta d theta, integration cos 2 theta d theta, correct? Let us take integration one by one. This is I0 upon 4 pi as it is, correct? And now integration 1 d theta, it is theta, from 0 to 2 pi, from 0 to 2 pi. Now, don't you know, derivative of sin theta is cos theta, speak reverse, integration of cos theta would be sin theta. So, integration of cos is nothing but sin of 2 theta, because here is cos of 2 theta, and integration would be sin of 2 theta divided by coefficient of theta, which is 2, from 0 to 2 pi, from 0 to 2 pi. Come on, this part as it is, instead of theta I am supposed to write the upper limit, which is 2 pi minus, come on, instead of theta I should write 0. 1 by 2 as it is, come on, sin as it is, instead of theta I should write upper limit, which is 2 pi, 2 pi into 2, that is 4 pi. After putting minus sign, instead of theta we should write 0, 0 into 2, 0. So, it is now sin 0. Now, this part as it is, 2 pi minus 0, that is 2 pi, 1 by 2 as it is, sin of 4 pi is 0, minus sin of 0 is also 0. 0 minus 0, 0, 0 into this will be 0, pi will cancel, 2 2s are 4, so it is I0 by 2. So, what is intensity of light coming out of this tourmaline plate? It is found to be half of intensity of light made incident on it. Come on, intensity of emergent light is half of intensity of incident light, okay? Now, 1 by 2 means nothing but 0.5 into I0. If you want the value in percentage, you should multiply by 100%, and if you do that, it will come out to be 50% of I0. So, 50% of this incident intensity will be transmitted intensity, correct? Intensity of transmitted light is 50% of intensity of incident light, okay? Fine. Now, read the statement of number 11. Read it? Look. According to Malus law, I equals to I0 cos square theta. This angle theta is given to right now how much? 60 degree. Put it here. Come on, theta is 60 degree. cos 60 degree sin 30 degree, which is 1 by 2, its square will be 1 by 4 into I0, that is I0 by 4. Now find out I upon I0. It will be 1 by 4. I upon I0 will be 1 by 4. But ratio of intensities is as good as ratio of squares of amplitudes. Ratio of intensities means what? Ratio of squares of amplitude. So I should write in place of this, come on, E square upon E0 square, that equals to 1 by 4. Now take square root on both the sides. Square root of this will be E upon E0. Square root of this will be 1 by 2. Fine. And now I just take dividendo. Come on. In the numerator. Correct? So it is now E minus E0. E minus E0 upon E0. Take dividendo here in the numerator. 1 minus 2 upon 2. 1 minus 2 upon 2. 1 minus 2, that is minus 1 upon 2. Now just reverse the order. When you make the order reverse, then the minus sign will come out. That minus and this minus will become plus. So here now you can write E0 minus E upon E0. Minus minus has become plus 1 by 2. And now what is this? E0 minus E means what? Initial amplitude minus final amplitude. This will give you decrease in amplitude. Let it be shown by symbol delta E upon E0. That equals to 1 by 2. And now tell me, just multiply on both the sides by 100%. When you multiply 100% here, here also you have to multiply. And change in any physical quantity divided by its original value, multiply by 100%. This whole term will give you percentage decrease in amplitude. Percentage decrease in amplitude. And that percentage decrease in amplitude we have found to be 100% divided by 2, that is 50%. 50%. Right? Fine. Read now number 12. Read it. Look. According to Brewster's law, you know n equals to tan theta p. N equals to tan theta p. Tell me what is n? It is refractive index of given denser transparent medium with respect to rarer medium. Here rarer medium is water, denser medium is glass. So it is refractive index of glass with respect to water. And now if it is n21, then in third semester you are writing n2 upon n1. Similarly here NGW, then NG upon NW. And right hand side as it is, tangent as it is, but this angle of polarization is nothing but some sort of angle of incidence. So I am writing I. And now NG as it is, what about NW? It is refractive index of water, 1.33 given to you. And tangent of I, this angle of incidence is given to 51 degree. How much? 51 degree. Fine. Now this 1.33 you can transfer here. Multiply by tangent of 51 degree, it is 1.235. This into this answer is 1.64. What is this? Absolute refractive index of glass. Correct? Fine. Read now number 13. Read it. First of all, they have used red light, for which wavelength they have given 6500 angstrom, for which at a particular angle first order minimum takes place. Okay, let us now apply condition of minimum. Condition of minimum. It was sin theta m equals to m lambda upon d. Because you are talking about first order minimum, I should write m equal to 1. So sin theta 1 will be lambda upon d. Lambda upon d. This sign as it is, this is angle of diffraction for first order minimum, which they have given 15 degree. And lambda is the wavelength, for red light they have given 6500 angstrom, convert it into meter, multiply by 10 raised to minus 10. And now this D will be obtained in meter, which is width of a slit. Fine. Sine of 15 degree, they have given 0.2588, or otherwise you can find out from table of natural sine. It is 0.2588. This part as it is, find out D, it comes out to be 2.512 into 10 raised to minus 6, this many meter. Fine. Now they have changed the light. Instead of red light, now they have used violet light. For violet light, it so happens at the same point we get what will be the what will be the minimum or maximum, that is what we have to find out. At the same point when we use violet light, which order minimum or which order maximum will be obtained, that is what we have to find out. So now on the same slit, instead of red light, we are making incidence of violet light. At that time, at that previously mentioned point, what will take place, whether it will be minimum or maximum, that is what we have to find out. Come on. First of all, for minima, what is the condition? Sin theta is equal to m lambda upon d, correct? And then you just find out d sin theta upon lambda. D sin theta upon lambda, it should be equal to m. D sin theta upon lambda should be equal to m. But what are the values of m? 1, 2, 3 dash dash dash. And suppose maxima takes place. Then for maxima we know the condition sin theta equals to m plus 1 by 2 lambda upon d. Just find out d sin theta upon lambda from here also. You will get it m plus 1 by 2. But what is values of m? Values of m are 1, 2, 3 dash dash dash. If you place here 1 plus 1 by 2, that is 3 by 2. Place 2 plus 1 by 2, that is 5 by 2. Place 3 plus 1 by 2, that is 7 by 2 dash dash dash. So what I mean to say, to decide whether particular order minimum or maximum would take place at a given point, what you should do, you should find out same ratio. Every time, come on, you should find out d sin theta upon lambda, here also d sin theta upon lambda. In case of Fraunhofer diffraction, to find out minimum or maximum, you should find out this ratio, and if this ratio comes out to be 1, 2, 3 dash dash dash, then minima would take place. And if this ratio comes out to be 3 by 2, 5 by 2, 7 by 2 dash dash dash, then particular order maximum would take place. So let us see what is the value of that ratio in our case. Look, here d sin theta upon lambda, but because we are using violet light, I am just putting lambda v for violet, okay. Come on, d, same slit we are using, so same width, 2.512 into 10 raised to minus 6 into sin theta. Theta is 15 degree, and sine of 15 degree is 0.2588. Sine of 15 degree is 0.2588. Lambda b, wavelength of violet light, they have given 4333 angstrom, converted into meter, multiply 10 raised to minus 10. Don't forget this d value we are using in meter, so this lambda must be converted into meter. Simplify, answer is 1.5. 1.5 means what? 3 by 2. And if it is 3 by 2, which is the value among these values, so there must be maximum which will take place at the mentioned point on the screen, okay. So come on, and which order maximum? See, when you write here 1, then only you will get 3 by 2, correct. So when you are writing m equal to 1, meaning thereby you are talking about first order maximum. So at the mentioned point, come on, first order maximum would take place at previously mentioned point on the screen, okay, fine. Now we begin with MCQs from exercise. Kindly read the statement of first MCQ. Read it? Come on. There are 4 formula for path difference. R2 minus R1 or d sin theta or d tan theta or x into small d upon capital D. Right now I am using this formula of path difference d sin theta, and because they are talking about third bright fringe, I should use the condition of constructive interference. Come on, path difference should be equal to n lambda for constructive interference. Path difference is d sin theta, and here it is n lambda. Now D is the distance between two slits in Young's experiment. It is given to you 0.2 millimeter, converted into centimeter, multiplied 10 raised to minus 1. Sin theta as it is, because they are talking about third order bright fringe, I should write n equal to 3. The wavelength of the light used is 5000 angstrom, converted into centimeter, multiplied 10 raised to minus 8. See, these both the values are converted into centimeter. Okay, fine. And now find out sin theta. It comes out to be 0.0075. I told you, whenever sin theta value comes out to be 0.05 or less than that, whatever is the value of sin theta, same value you should take for theta, but in radian. Right now, this value of sin theta, we can see it is less than 0.05. So, same value should be taken as theta value, but in radian. So, theta value in radian will be right now 0.0075 radian. What is this theta? Angular position for third order bright fringe. Angular position for third order bright fringe. Okay, fine. Now read number 2. Read it. They are talking about fourth order dark fringe. Fourth order dark fringe. Dark fringe, zero intensity, destruct interference, path difference should be 2n minus 1 lambda by 2. Path difference is x into small d upon capital D. And come on, for destruct interference, what is path difference? 2n minus 1 into lambda by 2. 2n minus 1 into lambda by 2. Got it? Fine. So now you are talking about fourth order dark fringe. So I should write n equal to 4. x4 into d upon capital D. x4 into d upon capital D. When you write n equal to 4, 4 to the 8 minus 1, that is 7 into lambda upon 2. Leave this x4 as it is, which will give you distance of fourth order dark fringe from central bright fringe, which we have to find out. Come on, small d, distance between two slits is given to 0.4 centimeter. Capital D is distance between slit and screen, they are given 100 centimeter. 7 by 2 as it is. 7 by 2 as it is. What about lambda? They have given wavelength of light used is 5000 angstrom, converted into centimeter, multiplied 10 raised to minus 8. Because you have taken all the distances in centimeter, then naturally this x4 will be obtained in centimeter. It comes out to be 4.37 into 10 raised to minus 2 centimeter. This gives you distance of fourth order dark fringe from central bright fringe. Read now number 3. Read it. What is the formula for fringe width? It is beta equals to x bar upon 2. Beta equals to x bar upon 2. And what is x bar? Lambda into capital D upon small d divided by 2. Come on, lambda wavelength is 5000 angstrom, converted into centimeter, multiplied 10 raised to minus 8. Capital D is distance between slit and screen, it is 100 centimeter. 2 as it is. This is distance between two slits, it is 0.1 millimeter, converted into centimeter, multiplied by 10 raised to minus 1. Find out this, it comes out to be 2.5 into 10 raised to minus 1 centimeter, but 10 raised to minus 1 centimeter is nothing but 1 millimeter, so this is 2.5 millimeter. Fine. This is fringe width, okay? Come on, read number 4 now. Come on, again recall the formula of fringe width. Beta equals to lambda into capital D upon 2 into small d. Lambda into capital D upon 2 into small d. Now new fringe width, I just show it by symbol beta dash. See, light is not changed, so lambda will remain constant. But distance between slit and screen has been made double. So instead of d, I am putting 2d. This 2 as it is. And distance between two slits is made half. So instead of d, I should write d by 2. And now tell me, denominator will go in the numerator. So 2 2s are 4, lambda d upon 2d. Come on, lambda d upon 2d. This 4 as it is. What is this lambda d upon 2d? Lambda d upon 2d is nothing but beta, which is original fringe width. Correct? So new fringe width is, come on, 4 times original fringe width. That is, fringe width value will increase to 4 times its initial value. Fine. Read number 4. Come on, fringe width is beta equals to lambda d upon 2 into small d. But earlier red light was used and now they are using blue light. But you know, wavelength of blue light is smaller than wavelength of red light. Because this lambda is going to decrease, naturally when lambda will decrease, come on, beta will decrease. That is, fringe width will decrease. When fringe width goes on decreasing, what will happen? All the fringes will become more narrow, correct? They will become narrow and the whole pattern would contract. That is, they will be just getting adjusted conjustedly, correct? So within the short distance now they will be accommodated, so they all will become congested. Fine. Come on my dears, proceed further. Read the statement of MCQ number 6. Read it? Fine. See here what have they done. In Young's experiment, you must have remembered we had two slits S1 and S2. Now they have covered both the slits by two different transparent sheets having thickness is T1 and T2, having refractive indices N1 and N2. And when that job is done, at that time, you know what have they given? That central bright fringe remains at the same position. So there is no net displacement of central bright fringe. Central bright fringe remains there only, it does not shift. If it is so, then what is the relation between T1 and T2? That is what we have to find out. Look, earlier in the same chapter, in the numericals, we had obtained this formula. Remember? Out of two light rays which are superposing on some point on the screen emitted from two slits S1 and S2, out of those two light rays, if in the way of one of the light ray, if you place a transparent sheet of thickness T and refractive index N, then what was the net path difference between superposing light rays? Net path difference was T into N minus 1. T into N minus 1. Wait. Now this net path difference is equal to x into small d upon capital D, where remember x is displacement of central bright fringe. Displacement of central bright fringe. Fine. Now tell me, let us apply this equation for two given sheets. For first sheet, come on, instead of T I am putting T1, instead of N I am putting N1, instead of X I am putting X1. For second sheet, come on, instead of T I am putting T2, instead of N I am putting N2, instead of X I am putting X2, correct? And now, if you introduce two sheets in the way of both the light rays, then what will be the net path difference now? To find out net path difference, you should take subtraction between these two. Come on, this minus this would be net path difference. So net path difference is this minus this. Here it is, this minus this. And that will be equal to this minus this. But once you take this minus this, d upon d can be taken common. Inside the bracket, x1 minus x2. Here it is, x1 minus x2. Correct? And now tell me, what have they given? When they do so, when they introduce two sheets in the way of two light rays, it so happens the central bright fringe remains at the same position. If central bright fringe does not shift, then net displacement of central bright fringe should be taken 0. So here this value is given to us 0. Just put x1 minus x2 equal to 0 here. 0 into this will become 0. Transfer this from minus, it will become plus. And now find out T1 upon T2. It will be N2 minus 1 upon N1 minus 1. N2 minus 1 upon N1 minus 1. This is the required condition relating T1, T2 and N1, N2. Got it? Now kindly read the statement of question number 7. Read it? Look. Again, if in the way of one of the two light rays which are superposing at some point on the screen in Young's double slit experiment, then net path difference between superposing light rays is T into mu minus 1. Instead of n, I am just putting mu. Whether you write n or mu, interpretation remains same. Right now mu is refractive index, T is the thickness. But now, why you are matching that net path difference with n lambda? Because they have said central fringe remains bright only. If central fringe remains bright means maximum intensity. Maximum intensity means constructive interference. Constructive interference means path difference should be n lambda. That's why this path difference is matched with n lambda. Suppose they say that central bright fringe, in place of central bright fringe, suppose they say that particular order dark fringe is taking place. Suppose, then you will match the same path difference with not n lambda. At that time you will recall the condition of destructive interference. It was 2n minus 1 into lambda by 2. Got it? Right now for constructive interference, I just equate this with n lambda. Fine. Now they have asked minimum thickness. So instead of T, I am just putting T minimum. This part as it is, and because lambda is constant and you want minimum value of T, so here n value should be minimized. So you should take n minimum. Now this part as it is, mu refractive index of the plate they have given 1.5. What are the values of n in the condition of constructive interference? What are the values of n? 0, 1, 2, 3, dash, dash, dash. Among 0, 1, 2, 3, dash, 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 what is the minimum value? 0. So you should take here 0, na? Minimum value 0. No, you cannot take, because the moment you take n equal to 0, this T thickness will be 0. Can there be any plate having 0 thickness? No, such a plate does not exist having 0 thickness. So after 0, what is next minimum possible value? It is 1. So I am writing n minimum equal to 1 into lambda. Mu is given to us 1.5. Now simplify. 1.5 minus 1 means 0.5. 0.5 means 1 by 2. Transfer this 2 over here. It will become 2 lambda. It will become 2 lambda. So minimum thickness in this case is double than the wavelength value of the light which is used in the experiment. Okay. T minimum comes out to be 2 lambda. Got it? Read number 8 now. Read it? Come on. For observing any object very minutely in very much detail, you must be in a position to have its very clear image. To increase the clarity of image, you should decrease the diffraction effects. To decrease the diffraction effects, you should reduce the ratio lambda upon d. And how can you reduce the ratio of lambda upon d? You can reduce provided you are using a light of shorter wavelength. So, for a light of shorter wavelength, come on, lambda will decrease, lambda upon d will decrease, amount of diffraction will decrease, image will be obtained more clear, then you can see the things very clearly, correct? So, we should use, come on, light with a short wavelength, that is your final answer. Read number 9 now. Read it? They are talking about angular width of central maximum. And earlier in the theoretical part, I had derived the formula of angular width of central maximum. It was 2 lambda upon small d. Now tell me, in the formula of angular width of central maximum, capital D does not appear. Capital D does not appear here, meaning thereby width of central maximum does not depend on the distance between slit and screen, because capital D does not appear here. Okay, fine. Read number 10 now. Read it? They are talking about maximum. So recall the condition for maximum. Sin theta m dash should be equal to m plus 1 by 2 into lambda upon d. And because they are talking about second order maximum, I should place value of m equal to 2. Put m equal to 2 here. Put m equal to here. 2 plus 1 by 2, that is 5 by 2. So it is 5 lambda upon 2d. 5 as it is. What about wavelength of light? They have given 6000 angstrom. Just convert it into centimeter, multiply by 10 raised to minus 8, and mind well, because this you are taking in centimeter, this also must be taken in centimeter. 2 as it is. This is the width of the slit, which they have given 0.01 centimeter. Simplify, answer is 0.015. And didn't I tell you, whenever you get sin theta value either equal to 0.05 or less than that, then whatever is the value of sin theta, same is the value of theta in radian. This value is definitely less than 0.05. So in place of sin theta 2 dash, I can write theta 2 dash, but that value of theta dash should be taken in radian. Fine. Read number 11 now. Read it? Come on. We should use oil immersion objective for what purpose? By using oil immersion objective, do you know, we are minimizing the value of, come on, linear limit of resolution. And if dm value is decreased, then 1 upon dm will increase. That is, linear power of resolution will increase. When you increase the linear power of resolution, then you can see the images of two closely lying point objects also very separated. Okay, fine. Now read number 12. Read it? Come on. Here is water surface. Here is incident light ray coming from sun, and this is the angle of incident because it is the angle between incident light ray and normal. And now tell me, because reflected light ray becomes completely plane polarized, this angle of incidence must be equal to angle of polarization. And whenever reflected light ray is completely plane polarized, you can definitely use, come on, Brewster's law. N equals to tan theta b. N equals to tan theta b. What is value of N? Refractive index of water right now, they are given 1.327, and theta b is angle of polarization. Actually, it is some sort of angle of incidence. So, instead of theta b, I may write I. Now, tangent of I is this much, 1.327. Then using the tables of natural tangent in the log table, you can find out value of I. It comes out to be 53 degree. How much? 53 degree. And now tell me, from the figure, if you make addition of these two angles, correct? Addition of these two angles will give you this much angle, which is 90 degree. So, I plus alpha equals to 90 degree. I plus alpha equals to 90 degree. Put I value, come on, 53 degree plus alpha equals to 90 degree. Come on, find out alpha. It is 90 minus 53. 90 minus 53 is how much? 37 degree. Correct? Come on, read number 13. Read it? Look. Here is incident light ray. This is reflected light ray. This is refracted light ray. In the absence of this denser medium, this incident light ray might have propagated along this straight path. But because of presence of this denser medium, it undergoes refraction, and then after it propagates along this path. So, this much is the angle of deviation. This much is the angle of deviation. So, incident light ray is getting deviated by angle delta. Okay. Angle made by refracted light ray with the normal drawn at the point of refraction is known as angle of refraction. Let it be shown by symbol small r. Now, tell me, if you take addition of these two, it will be this much, and this much angle is equal to this much because they are vertically opposite, correct? But this angle is nothing but angle of incidence I. So, these two when added should give you angle of incidence. So, this total angle is I equals to R plus delta. I equals to R plus delta. What is I right now? Angle of incidence, but it is that angle of incidence at which reflected light ray becomes completely plane polarized, then it must be taken equal to angle of polarization. So, instead of I am putting theta b. R equals to, by formula in Brewster's law we had seen, R equals to 90 minus theta p. Delta is angle of deviation which they have given in the statement 22 degree. Now, minus theta p if we transfer here will become plus theta p plus theta p, that is 2 into theta p. 90 plus 22, it is 112 degree. Find out theta p, 112 upon 2, that is 56 degree. 56 degree. And now, angle of refraction R equals to, in Brewster's law, 90 minus theta p. 90 as it is, theta p is 56 degree. 90 minus 56, that comes out to be 34 degree. So, we were looking for angle of refraction which has come out to be 34 degree. Now, read number 14. Read it? Come on, angular power of resolution is nothing but reciprocal of angular limit of resolution, and it is 1 upon alpha minimum. Come on, alpha minimum formula is 1.22 lambda upon capital D, which goes up in the numerator. And now, because capital is constant for a given telescope, 1.22 is constant, then relation between P and lambda would be P varies as 1 upon lambda. For inverse proportionality, you know 1 to 2, 1, 1 to 2, 1. P1 upon P2 equals to lambda 2 upon lambda 1. And now first wavelength you are given 4000 angstrom, second wavelength is 5000 angstrom, 5000 upon 4000, that is 5:4, 5:4. Read number 15 now. Read it. Angular power of resolution by formula, it is d upon 1.22 lambda. This diameter of objective of telescope, they have given 1.22 meter. Once you are taking this in meter, this also must be taken in meter. 1.22 as it is, lambda in meter, they have given, come on, as such they have given 5000 angstrom. But we must convert into meter. Angstrom to meter multiply by 10 raised to minus 10. Simplify. Answer is 2 into 10 raised to 6. But unit of angular power of resolution is 1 upon radian, because this is formula which is applicable only in the radian value. So this alpha minimum is in radian. So unit of angular power of resolution should be 1 upon radian. 1 upon radian, that is radian inverse. Radian inverse. In textbook they have not mentioned the unit. You must mention radian inverse. Now read number 16. Read it? Come on. This angle they have given 33 degree. Then how much should be this angle? This total angle is 90 degree. 90 minus 33, it will be 57 degree. And this is the angle between incident light ray and normal drawn at the point of incidence. It must be angle of incidence. So I is equal to 57 degree. Moreover, come on, this refractive index they have given for this denser medium, come on, 1.54. And tangent of I, just I want to find out. What is I right now? 57 degree. Tangent of 57 degree comes out to be 1.54. I mean to say whatever is the value of n, same is the value of tangent value of angle of incidence. And don't you know n equals to tangent of angle of incidence? N equals to tangent of angle of incidence. What is it? It is Brewster's law. If Brewster's law is obeyed, meaning thereby reflected light ray must be completely plane polarized. And whenever a ray of light is getting reflected and becomes completely plane polarized, at that time it contains only those E vectors which are perpendicular to plane of incidence. Perpendicular to plane of incidence means only sigma components, and that's why I am just putting dots, correct? Now tell me, in the way of this refracted light ray, we just place some polarizer, some tourmaline plate whose optic axis is supposed like this. These are the E vectors, and they are just being incident to the plane of incidence this way, correct? They are oscillating this way, perpendicular to plane of incidence this way. That's why I am putting dots, only sigma components this way. And now suppose initially the optic axis is like this. If optic axis is like this, then all the E vectors are parallel to this optic axis, so they will pass. When all the E vectors are passing, then naturally intensity of reflected light would become, intensity of transmitted light would become maximum. Intensity of transmitted light would become maximum. But then after, what are you doing? You are just giving a rotation like this, correct? And when you give 90 degree rotation, then all E vectors will be found perpendicular to this optic axis. If all E vectors are incident on the optic axis perpendicularly, all of them will get absorbed. Not a single E vector comes out. So intensity of transmitted light would become 0. Earlier intensity was maximum and now it has become 0. So intensity of transmitted light will decrease from maximum to 0, and then after again it will increase, correct? Fine. So answer is, come on, light ray, reflected light ray would be completely plane polarized, and after that what is the final answer here? Intensity of transmitted light. Intensity of transmitted light would first of all, come on, decrease from maximum to 0, and then after again it will increase. decreasing from maximum to 0 and again increasing. Okay, that is the answer. Let me write here. Come on. For number 16, I am writing further final answer. Final answer. Come on. Intensity of transmitted light. Intensity of transmitted light decreases to 0 and then increases. Correct? Fine. So come on. Intensity of transmitted light, come on, decreases from maximum to 0 and then again if you rotate further it will increase. Suppose some student is thinking this way, that if these are the E vectors, suppose initially optic axis like this, suppose, then intensity of transmitted light would be initially 0 and then after as you rotate by 90 degree, gradually it will increase. So that answer is also correct, increasing from 0 to maximum and then decreasing. That is also correct, but it is not there in the options. It is not there in the option. That's why among the given options, this option is correct, okay, which is the last option. Okay, fine. Now, read number 17. Read it? Fine. Now tell me, here if I make unpolarized light incident having intensity I, then in one of the illustrations in this chapter we had proved that the intensity of light coming out of this stationary tourmaline plate would be I by 2, So what we had done at the time, we had kept the tourmaline plate at rest, stationary, and the unpolarized light is made incident, correct? At that time, the intensity light coming out of the tourmaline plate, we had proved in one of the illustrations, it was reduced by 50%. So it was becoming I by 2, correct? Here I0, then you can write here I0 by 2, here I, then you can write I by 2. Simple. Now that light which is made plane polarized is now made incident on second polarizer, okay? Now that second polarizer, suppose it is like this, then through this second polarization, what intensity of light will be getting transmitted, that is given by Malus law. Here intensity of light would be intensity of light made incident on it multiplied by cos square theta, correct? Here first term would be intensity of light which is made incident on this polarizer, which is I by 2 into cos square theta, okay, according to Malus law. Come on, here if it is I0, then you may write I0 cos square theta, correct? If here it is I by 2, then you may write I by 2 into cos square theta. Now in the statement they want to say that this intensity becomes 1/3 of this intensity. So this intensity is I by 2 cos square theta, and it is to be taken now as per the correction 1/3 of this. So 1/3 of I. Now I will cancel, giving you cos square theta equals to 2 by 3, and 2 by 3 comes out to be 0.6667, correct? Take now cos square theta equals to 1 minus sin square theta, this part as it is, minus sin square theta you take it on right hand side will become plus, and this you can take on left. Come on, 1 minus 0.6667 would be 0.3333, and now take square root of this, that is sin theta. Square root of this comes out to be 0.5773, and now from the table of natural sine you can find out that angle for which sine function value is exactly this much or nearest to that. And that value of theta we get from the natural sine table, it is 35.3, that many degree, correct? Earlier we had brought the answer 54.7, something like that, but that is wrong. Now we are taking this intensity, not 1/3 of this, we are taking 1/3 of this, okay? And then the answer is this 35.3, that many degree.